Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. We have been discussing about the network modeling for three-phase power network. So, in the last class, we have first derived the equation for injected power at bus I corresponding to phase P, and that P is actually ABC, and this expression is given here that IIP is equal to L. And then of course, and then we can see that essentially in the expression of any current, injected current at any bus corresponding to any phase P, A, B, C. So essentially there are three n terms if there are n bus system. And then we have noted that the elements of the Y bus matrix as well as the bus voltages are all complex quantities. So then therefore we have noted down their magnitude as well as angle. So then therefore we said that YIJPL, Ij is equal to 1 to n, and PLABC, that would be is equal to YJPL, that is the magnitude part, and it will have an angle alpha IJPL. Similarly, the voltage VJL, where J actually varies from 1 to n and L varies from ABC. So that is also given by VJL angle theta JL. VJL, that is the magnitude part, and theta JL is the angle part. So using this magnitude as well as the angle representation, we ultimately find out the expression of IIP is equal to L ABC summation of L ABC, and then followed by summation of J 1 to n, then YIJPL VJL theta JL plus alpha IJPL. And then we have said, so now after we have actually derived the expression of the injected current at bus I corresponding to phase P, then we have talked about the injected complex power at bus I corresponding to phase P. SIP is equal to PIP plus JQIP. So here when J is used not as a subscript, it actually denotes the complex operator, and PIP is nothing but the injected real power at bus I corresponding to phase P, and QIP is injected reactive power at bus I corresponding to phase P. So, and again I can essentially write down that PIP is basically, I can write down is actually P gen IP minus P, or rather I should say there is no need to use, I can say that this is PGIP this, and then minus PLIP, where PLIP is actually nothing but PLIP is basically the real load at bus I corresponding to phase B, and this is of course real generation at bus I corresponding to phase B. So obviously if at any bus PGIP is 0, so then therefore PIP would be is equal to minus PLIP. So all these things are known. Similarly, I can write down that QIP is QGIP minus QLIP. Again, let us define. So this is reactive generation, power generation at bus I corresponding to phase B, and this is reactive load at phase B. So, and we also know that SIP is equal to PIP plus JQIP, and that would be given by VIP into IIP conjugate, where this star denotes complex conjugate, right? So now we have to put this. So then therefore SIP is equal to VIP, that is the magnitude angle theta IP, this, and then we have L is equal to A B C, G is equal to 1 to N, Y I J P L V J L, angle alpha I J P L plus theta J L. So this is IIP. So this whole star. Now because now here we can see that there are basically two summations, and basically none of these summations has got the index I, neither P. So then therefore we can simply take them inside, and then because this is complex conjugate, so then this turns out to be L is equal to A B C, J is equal to 1 to N, then I can say that VIP VJL YIJPL, then angle theta IP minus theta JL minus alpha I JPL. Right. So from here, if I, and that is equal to PIP plus JQI. So then therefore, if I now match the real as well as the imaginary part at the both sides, so I get PIP is equal to L A B C, J is equal to 1 to N, VIP VJL YIJPL, then cosine theta IP theta JL alpha IJPL, and QIP L is equal to A, B, C. J is equal to 1 to N VIP VJL. So this is it. So these are the expressions. So these two expressions, these are called power flow equations in three-phase system. Now, so I mean these are the three-phase system. Now suppose just simply recollect the power flow equation for a single phase system. For single phase system, for single phase system, single phase or balanced system, I know that Pi would be given by, because it is a single phase or balance, so then therefore there is no question of any kind of phase. So it is simply given by Pi is equal to J is equal to 1 to N, then Vi, Vj, Yij, then cosine theta I minus theta j minus alpha ij. So I mean that is the standard expression we already know, and if we just now simply compare this expression with the expression of PIP, we can see that these are just the same. Both the expressions are same. Here it is Vi, it is VIP, because when we are talking about three-phase system, not only we have to think about the bus number, but we also have to think about the phase. So we talk about VIP, then it is VJL, that is the Lth phase of jth bus. Then YIJPL, that is the uh, element of the Y bus matrix corresponding to bus Ij and phase PL. And what do they mean? We have already discussed in some earlier class. And then we have got cosine theta I in the case of single phase, it is theta IP again, bus I phase P, minus theta j in the case of single phase, in the case of three phase theta j L, and then minus alpha ij. Alpha ij is nothing but the angle of the element of the Y bus matrix corresponding to bus I and j in the case of single phase system, and in the case of three phase system it would be bus ij and phase PL and alpha ij PL. So then therefore we can see that the expressions are same for both the cases. Only thing is that in the case of three phase system also the phase notations come into picture. So that's why the number of terms in the case of a three phase system increases. So these are the power flow equations in three phase system. So now with these power flow equations, so then we are now ready to go into the more details of the load flow analysis of a three phase system. Now to understand that, first let us understand that, I mean basically what are the number of unknowns, unknown quantities. So we will talk about in terms of three quantities. First is unknown quantities. We have to understand that what are the unknown quantities. Then we have to understand that what are the specified quantities, that is what quantities we know, and of course these particular specified quantities must be in terms of the unknown quantities. That means these specified quantities will give us some equations, specified quantities. These are also nothing but the known quantities. Then the equation, we have to talk about the equations relating unknown and specified quantities. And then the last is the solution process. So we have to talk in terms of these four issues. Once we understand these four issues, so then we would be able to do the load flow analysis. So first let us discuss about the unknown quantities. So to understand that, let us take a very simple 3 bus system. So bus 1, bus 2, bus 3. So this is bus 1, bus 2, bus 3, then phase A, phase B, phase C. So for bus 1, the voltage magnitudes are angular V1A, V1B, V1C, and angles are theta 1A, theta 1B, theta 1C. For bus 2, V2A, V2B, V2C, and then theta 2A, theta 2B, theta 2C, and then V3A, then angle theta 3A, V3B, angle theta 3B, V3C, angle theta 3C. So for each bus there are actually basically 6 quantities: angle of phase A voltage, phase B voltage, phase C voltage, as well as the magnitude of phase A voltage, phase B voltage, phase C voltage. So then therefore for n bus system, so for each bus I, my unknowns are VIA, theta IA, VIB, theta IB, and VIC. Theta IC. So total 6 quantities. And for I, and I goes from 1 to n. So then therefore there are total 6 n quantities of interest. So total, so therefore 6 n quantities of interest. So we have to know by some means these 6 n quantities, and if we know this, all these bus voltage magnitudes and angles, so we would be able to calculate any other quantity. Now let's see in a practical power system what do we know. I mean, do we really have to solve all of them, or do we have to not? So for that we have to understand certain things. Let's take a very simple system, that bus 1, bus 2, bus 3, and let's say bus 4. Just 4 bus system. Please note all of them are 3 phase system. I am just not drawing them. So these are all 3 phase system. So this, so bus 1, bus 3, bus 2, bus 4. So all these buses are 3 phase buses, are 3 phase buses. So then therefore all these buses have got voltage, magnitudes and angle for, let's say, V1A, V1B, V1C, theta 1A, theta 2B, theta 2, 3, and etc. And suppose that there is one generator here connected at bus 1, and another generator is here connected at bus 2, and there are loads at bus 2 and at bus 3 and bus 4. So at bus 1 and bus 2 there are 2 generators, and at bus 3 and bus 4 there are loads. Now at bus 3, loads means that these are 3 phase loads. So then therefore loads are, I can say that it is essentially PL3A, then PL3B, PL3C, then QL3A, QL3B, QL3C. So these are real power load, these are reactive power load at bus 3. So real power, this is reactive power loads at bus 3. So this is bus 3. Similarly at bus 4 I have got loads as PL4A, PL4B, PL4C, and then QL4A, QL4B, QL4C. So this is again real load, this is again a reactive load. Correct? Now please note, if there is no load at any bus corresponding to any phase A, so we will say that these loads are 0. And we are also assuming that at bus 3 and bus 4 there are no generation. So then therefore for all these buses I can say that PIP is equal to minus PLIP, and QIP is equal to minus QLIP. Here I is varying from 3 and 4, and P is A, B, C, right. So therefore the injected power at bus 3 corresponding to phase B would be is equal to minus PL3B. Similarly, injected reactive power at bus 4 corresponding to phase C, that is Q4C, would be is equal to minus QL4C, correct. And we know from the we know from our earlier knowledge from power system analysis that if I know all these loads, I cannot really specify all the generated powers for all these generators. One of the generators must be defined as the slack bus, and that particular slack bus will take care of the losses, as well as that slack bus will also compensate for any shortfall of generation if there is any. So, suppose for example I say that total load at bus 3 is say 100 megawatt, and total load at bus 4 is, let us say, 150 megawatt. So, then therefore I can say as an example, so then therefore if I say that let us say that 100 is equal to PL3A plus PL3B total load plus PL3C. So, basically total load, let us say for example this is 35, this is 30, this is again 35, suppose all are megawatt, all are megawatt. And let us say that total load at bus 4, so this is bus 3, and let us say that at bus 4 is total load at bus 4 is say 150. So, this is equal to say a PL4A plus PL4B plus PL4C. Say this is 60, this is 50, this is 40. So, these are all in megawatt. And similarly, of course, this reactive power will also be there. But then for the generator, we generally do not specify the reactive power, we only do specify the real power. So, then therefore, I can say now suppose that P gen 2, PG2, suppose I say that the total generation from bus 2, that is the generator 2, is say PG2 is say for example say 170 megawatt. So, that would be is equal to P, essentially the total generation PG2A plus PG2B plus PG2C. Now, here what happens is we said that PG2, that is the total generation, total real power generation by generator at bus 2. But then we really cannot really pre-specify that what would be the value of PG2A, PG2B and PG2C. That must be calculated after the load flow is solved. So, this aspect and the other aspects we will discuss in the next class. Thank you.